In this episode of Woodlands on the Web, we're going to be looking at AP Chemistry Unit 6, Thermochemistry Notes. So you can access this note packet in our OneNote notebook, and it starts out with quite a bit of vocabulary, all of which is important. However, I think that the most important thing I want to point out is this section on enthalpy. So we've already learned about enthalpy before and how it's the change in heat content in a system. And so in this particular unit, we're going to learn about different types of enthalpy, and it basically just depends on what kind of process you're talking about. So we'll be learning more about each of those momentarily. But the other thing I want to point out as well is this concept of standard conditions. So standard conditions are kind of like STP, where we knew that that's 1 atmosphere of pressure and 0 degrees Celsius or 273 kelvins. But standard conditions is basically referring to standard laboratory conditions. So we accept that as 1 atmosphere of pressure and 25 degrees Celsius, which is essentially room temperature. So that's something important that I would definitely like to point out, because for actual experiments, we're generally talking about standard lab conditions. Those are also sometimes known as SLC, for standard laboratory conditions. Okay, so first we're going to talk a little bit about energy and work, and you probably haven't heard of work since middle school science, but we are needing to be aware of this formula. So energy is related to the heat quantity plus the work involved, okay? Most importantly, you have positive work if it's done on the system and negative work if it's done by the system. Okay, this is also going to be related to pressure with respect to gases. As always, we know gases are the only thing that are really susceptible to pressure. So if you're talking about a gaseous system, then you might need to talk about pressure and volume in that regard. So our first example is going to be looking at the basic work equation. And so we're going to be looking for the change in energy for a system that's undergoing an endothermic process. And that's here, this is showing the work is done on the system. Okay, so that's going to be telling us whether Q and W are positive or negative. Okay, so endothermic process, we have this much heat going in, so that's going to be a positive Q value for us. And since this work is done on the system, that is a positive work value for us. So our delta E is going to be Q plus W, heat content plus work. So in this case, it's just going to be our 15.6 kilojoules plus 1.4 kilojoules, which is going to give us a total of 17 kilojoules of energy change in the system. Exercise 2 has us looking at the work associated with the expansion of a gas. So this is going to be our change in volume. We have a V1 and a V2. And our pressure is constant at 15 atmospheres. So the formula we had above was that work is negative of the pressure times the change in volume. Okay, and so change in volume is always going to be final minus initial. So it's going to be 64 minus 46. So our work is going to be negative 15 atmospheres times 64 liters minus 46 liters, which gives us a negative 270 atmosphere times liters is our unit. Okay. However, we also we want to turn this into kilojoules. So we have a conversion factor that allows us to change that from 270 atmospheres times liters. We can use our conversion factor, which should be found on your reference sheet, and it's 101.3 joules per liter atmosphere. So those units will divide out, and that's going to give us negative 273.5 kilojoules. Okay, so I actually converted that to the number of joules you get, I converted that to kilojoules there. Okay. So that would be the amount of work associated with that particular gas expansion. And finally, in exercise 3, we're going to put both of those concepts together. So we are calculating our delta E, but remember, in order to do that, we need to figure out how much work is involved first. Okay, and again, here's that conversion factor to use to get our work into joules so that we can figure out how many joules of energy the system is actually changing by. So using the same equation that we used in exercise 2, we have negative pressure times the change in volume. So that's going to be 1 atmosphere, because it says that we are at 1 atmosphere. So -1 times our change in volume. If you subtract those, you end up getting 5 times 10 to the 5th liters as your change in volume. And that's going to give you -5 times 10 to the 5th liter atmospheres. Okay, converting that to energy, or to an energy unit, we'll use that conversion factor of 101.3 joules per liter atmosphere to get that into joules, and we get -5.07 times 10 to the 7 joules. Okay, now that we have that, we can use our energy equation. So remember that that's Q plus work. So it gives us a Q value of 1.3 times 10 to the 8. So we have 1.3 times 10 to the 8 joules of heat content minus the, or I should say it's plus the amount of work. So it's technically plus a -5.07 times 10 to the 7 joules. And when we do that math, we end up getting 7.93 times 10 to the 7 joules as our final answer. If you want to convert that to kilojoules, that's fine. It's not particularly necessary in this case. All right, now we're going to get into looking at the enthalpy, or the change in enthalpy of a system or reaction. Okay, so for a reaction, remember we reviewed last unit these types of reaction profiles. So the enthalpy of the reaction, again, remember that that's the enthalpy of your products minus the enthalpy of your reactants. It gives you the overall enthalpy of reaction. So typically we find that with stoichiometry, but as you can see down here, there are actually a lot of different ways that you can find enthalpy, and we'll talk about at least a couple of those here in just a minute. Okay, again, the most common way that we find enthalpy is through using stoichiometry. We can consider our enthalpy as part of our chemical reaction or chemical equation. Okay, so first we're talking about adding some solid potassium hydroxide pellets to water. And since we have our heat listed on the product side, okay, that means that this particular reaction, or this dissolution of this solid, is going to give off heat energy. Okay, so it's an exothermic process, which is actually the second question. But because it's an exothermic process, that means the beaker is going to feel warmer to your hand. If you were holding that beaker in your hand, it will feel warmer as the heat leaves the system and goes out into the surroundings, which would be the beaker and the air. Okay, now let's calculate the enthalpy change for this dissolution. Okay, so we have 14 grams as our starting point. So that's going to be our given when calculating the enthalpy change for this particular amount of potassium hydroxide. Okay, so setting up our train tracks. We have our grams of KOH, and essentially because this has per mole in it, that means we're going to need a mole ratio somewhere, or we're at least going to need moles, right? So we have grams, and we're going to need to convert that to moles. So hopefully by now we're really comfortable with the fact that that means we're going to be using molar mass. Okay, the molar mass of KOH is 56.11 grams per mole. Okay, that makes our grams divide out. And then now we're going to use that enthalpy value as our last conversion factor. But we have to remember that if the process is exothermic, the delta H is negative. Okay, so I want us to make sure that by deciding that this is an exothermic process, we actually use a negative 43 kilojoules in our conversion factor, because that's going to tell us whether or not that heat is released or absorbed. Okay, so to be the most correct, we should be getting negative 10.7 kilojoules. So what that means for this particular question is that we will feel a difference of the equivalent of 10.7 kilojoules being released from this system. So this is going to conclude this first part of notes for this topic. If you would, please follow up with the remaining videos, but that's it for this particular episode of Woodlands on the Web. I hope you learned something. Thanks for watching.